Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of C++ Crash Course, we're going to be talking about the short string optimization inside of C++, specifically inside of the implementation by GCC. This is something that changes between compiler to compiler, so it'll be different in Clang than it is in GCC, and then other places have their own implementation of the short string optimization. But to really understand what the SSO is, right, we have to talk about strings and how big are strings to begin with, right, before we do anything. So let's go ahead and just compile this very simple code, right? So this sso.cpp, and all we're going to do is print out the size of a string, right? Simple enough. Okay, so let's go ahead and we'll just do G++, right, on SSO, right, and then we'll just end this with /a.out. That we compile and run at the same time. Okay, so the size of the string is 32 bytes, right? So we did size of, that gives us the size in bytes. Okay, so what is that actually made of, right? So what composes that 32 bytes, right? So there'll be a section of it that's dedicated to the data or pointing to the data. There'll be a size, capacity, and then there'll also be some extra bits left over, right? And so that's how you get to 32 bytes. So now we'll look at something more interesting, right? And the more interesting thing is what happens when we start actually creating strings that have characters in them, right? So what we're going to do is we'll uncomment these lines right here. And all we're going to do is create a string over and over and over, right? From 0 to, 0 is less than string size, we're going to go up to, say, 32 bytes. And we're going to create, it's a very simple string. It's just, I of whatever character we choose, so just X in this case. And then we'll go ahead and print it out. But we've got something special here, right? So we want to track something, and that's if we're doing dynamic allocation, right? So if we're allocating anything on the heap. So the heap is allocating, and dynamic allocation on the heap is somewhat of an expensive operation. So we'd like to avoid it as much as we can, and we're going to just mainly work on the stack. So what we'll do is we'll actually just overload the new operator, right? And every single time we'll just go ahead and print out allocating so many bytes, and then we'll just return malloc, right? So we've got our own implementation of new here. So we'll intercept any of those calls. Right, so let's go ahead and run this again, and let's see if we get anything surprising, right? So let's clear the screen. And let's go to the very top. Well, that's rather interesting. If we notice for a string size of 0 through 15, there's not actually any dynamic allocations that go on. This doesn't happen until we get to a string size of 16, right? Or we have 16 characters that we want to represent, right? So 16, 17, 18, we see that all of these requires an allocation, right? So it called that overloaded new function, right? So once we get past 15 characters, we start allocating stuff on the heap. Okay, so this is really what this short string optimization is about. So when we have a short string, say something between 0 and 15 characters, we can actually just keep it locally on the stack, right? And so this is beneficial for a number of ways because it's it's very, very fast on the stack. We don't have to do any allocation, and basically what we're doing is we're taking some of those extra bits at the end, specifically 15 of those bits at the end, and we're saying, okay, well, in situ, we'll just go ahead and store 15 characters, and if you need any more characters than that, okay, we have to do a dynamic allocation. But this is a really nice thing, right? So instead of having to do a dynamic allocation right off the bat, when we're going to create a new string, right, of whatever amount of characters, we only do it once we get past a certain point. So if we're working with mainly short strings, we get the short string optimization, right? And this actually has quite a number of nice implications and things other than strings, right? So if you can have these same kind of semantics for, say, a short vector optimization, that's also something that's kind of cool. If you can just keep that information locally on the stack and not have to do a dynamic allocation. Okay, so enough of the little aside there. Let's talk about performance, right? So why do we actually care about avoiding something like a dynamic allocation? Well, it's always good, when we're talking about performance, to talk about benchmarking, right? So if we want to actually understand performance and optimize things for performance, we have to benchmark, right? So, being able to theorize about things is good, but what really matters is what the counters say. So let's go ahead and go to benchmark.cpp. So this is a very simple benchmark implemented in using Google Benchmark. And all it does is, we're going to pass in this dense range, right? So we're going to go between a size string of 0 to a size string of 32, right? So the exact same print scenario we did. So up here, we'll go ahead and read in the string length. We'll create a vector of strings, right? And we'll just go ahead and resize the vector automatically, right? So we don't have to worry about, the vector having to do allocation, 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 right? We'll just go ahead and resize it ahead of time because we know that we're going to be using 10,000 spaces. So the next thing we do, right? So in this while loop, so we'll go ahead and we'll push back a bunch of strings, right? And we'll create it within this while loop because that's what we really care about profiling. So we'll go ahead and create a string of string length. So from 0 to 32, right? But each of these, 0, 1, 2, 3 will be on a different run. So we'll just be creating, say, 10,000 strings of length 0, 10,000 strings of length 1, 2, 3, 4, all the way to 32, right? And then we'll just push it back into the vector, right? And we'll see where, if we find any differences in performance, if we get to that same spot. So once we get to past a string length of 15, so past 15 characters, what does our performance look like in comparison, right? So let's go ahead and compile this. So we'll just do G++, right? And then benchmark, and then we do, I don't think we need the C++11 standard for this. I think we can just link it against L benchmark, and then L pthread, and then we can just set the optimization level to 3, -O, and we'll just call this a benchmark. All right, so let's see what happens here, right? So it's going to go ahead and start, right? So it's going one by one, and we're going to get our different results. We see that, for size 0, size 1, okay, it's about, what is that, 342,000, right? But fairly consistent, right, between all these. There's a little bit of variance here, right, between about, 409,000, 420,000. But notice, very big difference here after we get past 15, right? So once we actually get past 15, an input length of the string is 15. Okay, that's the end, right? So after we get past that, so this is where this is the end of the short string optimization. So we can only store 15 characters in situ inside of the string on the stack. So that means anything after this, we have to make a heap allocation. And we see that 16 and onward, for all these where we have to make heap allocation, it'll swing around a little bit, but you'll see that, it's going to, it's significantly slower once you start having to do a dynamic allocation, right? And we can even look at this from a specific, we can time this a little bit better and make it run for longer to get a better number here. So we can go ahead and do /benchmark, and then we can also do dash benchmark, and then, benchmark filter equals, and then string bench, right? And let's do it right on the edge, right? So let's see what 15 is, right? So string bench /15, and then we can also say dash benchmark min time. This is the minimum time the benchmark will run, right? And we can say that the minimum time is, say, 3 seconds. I think I got the flags wrong, right? So let's do maybe dash. Okay, there we go. So it goes ahead and runs this. It'll go ahead and run it for 3 seconds. So we'll see what it is on the edge, right? So we get about 459,000 nanoseconds, right? And so we can go ahead and run this for, let's move it from 15 to 16, right? That way we can get a better picture of that gap. And after 3 or so seconds, we see that, okay, well, it is clearly slower, right? It's at about 823, getting close to 824,000 nanoseconds. So once we pass that gap, we have to start doing dynamic allocations. All of a sudden, we're spending a lot more time, right? So, so short string optimization is something that's very interesting. Different, like I said, different compilers will implement it in different ways. I believe the Clang compiler, you actually get 23 bytes of in situ space to work with. There's also a great talk from CppCon about Facebook's own implementation of string, right, that has a larger capacity than GCC. But there's a lot of trade-offs associated with this, so I'll go ahead and link that video with a great explanation in it in the description below. As always, all this code can be found at github.com/coffeebeforearch. So we go to C++ Crash Course, and we go ahead and go to, if it will load for me, we'll go to optimizations, and then we go to SSO for short string optimization, short string, small string optimization. I've heard it both ways. Right, so we've got both the, our little overloaded new function here that shows off when the actual allocation occurs, right? And I believe this allocation happens at GCC 5 or later. I think 4 or earlier. I think 4 or earlier, there's not actually a short string optimization yet, right? And we also have the Google benchmark here. So check out Google benchmark as well if you're interested in running this one. But that's going to go ahead and do it for today. As always, I'm Nick. I hope you have a nice day.